So hello, everybody. I'm mainly working in the area of formal methods, and but got interested in machine learning. I've already been working in the field of grammatical inference, which can be seen as a field of a sub-area of machine learning. And in this talk, I try to exploit some synergies between these areas to tackle new challenges. So this was for the month of March. So here we'll only talk about one challenge that we tackled in the meantime, or try to tackle. And so this is joint work with a number of people, partly accomplished joint work, partly ongoing work within a German-French collaboration. And so in formal methods, usually we are given a program or a system, and we're also given a specification, a requirement specification to be fulfilled by the program. And so we would like to detect, preferably automatically, whether the program satisfies the specification. That is, whether all the traces, all the program traces that we can potentially observe satisfy the specification, like an error never occurs. And well, to do so, we can apply model checking. This is one popular approach in the field of formal methods. And what we do there is we represent the program as a transition system, which is sort of graph where the nodes represent the configuration, maybe of variables, and the edges represent some variable assignments or other actions like send a message, so that the whole graph represents the control flow of a system or of a program. And well, similarly, the specification, as we heard this morning by Michel, I think, specification can be described in natural language, but it can also be described in a formal language. And in that case, we can also compile it into a sort of transition system. Let me see here. Sorry, over here. And well, what model checking does is well, to take the program graph and the property graph, and well, it takes the product, and it turns out that all the traces of the program graph satisfy the property if and only if certain faulty configurations are not reachable in the graph. So we reduce this to a reachability problem in the graph. That's what roughly model checking does. And model checking goes back to the 80s and has had quite some success in academia, but also in industry. Maybe not as much as it would have deserved, but still it has reached some certain industrial acceptance. But there are cases in which I think we have already heard about black box systems today. There are cases in which the system as such is not accessible, so it's difficult or even impossible to come up with a model. So think of legacy software, or maybe the code is not open source, embedded systems where we have several heterogeneous components. That's rather difficult to come up with a faithful model and to apply model checking. So this does not work anymore. And in that case, we could resort to learning. So learning algorithm would interact with the system and eventually come up with a model that we can use for model checking as before. Okay, so and while the field of grammatical inference or model learning also goes back, or has its origins in the 50s maybe, but there's a particular algorithm, Angwin's algorithm, which plays a particular role in this field, and which also at the heart of a very nice survey article about model learning and model verification by Fritz van Drager, which is quite recent. So it shows that it's an emerging, well, it's still an emerging field. Okay, I will give you a glimpse of Angwin's algorithm. It's not so important to understand how it exactly works. Don't worry about the details, but rather to get an idea of how it interacts with the system so that we can embed it into a verification framework. So to apply it, so we assume that we are given a system in terms of of a language, the set of its traces. A language is a set of words, which represent traces of the system runs. So in this example, we have a very simple language of a two-letter alphabet A and B, saying that the second last letter should be a B, that's all. But in reality, of course, these letters A and B stand for something concrete, could be send a message, set a variable to a certain value, and so on. Yeah? But for example, let's consider something very abstract. And But note also that such a language can be considered as well, represented by its characteristic function, where we map every word that is in the language to 1 and every other word to 0. So in principle, this approach will also be applicable to classifiers, binary classifiers, but also multi-label classifiers, and we will, in fact, apply this later on to recurrent neural networks, yeah, which classify strings, which can assign, which accept strings or reject strings. So and the idea is that the learner interacts with this language in some way. I will come to this. And at some point comes up with a finite state representation. This is such a graph that we are looking for, a finite state representation that represents exactly the unknown language L. Yeah? And L is unknown, it's a black box system. And once we have this, we can apply model checking. So I give you an idea of how this works. So the learner will interact with the system, and it can ask membership queries. It can ask for any arbitrary word it wants, whether it's in the language or not. It's a membership query. So in practice, this will correspond to by giving inputs to the system and observe whether what it does with this. So this means that can also be applied to particular systems where we can somehow interact with the system, even though the global structure is not really known. And well, the information that it acquires in such a way is then organized in some data structure. It's actually a table. So for example, we will observe that the empty word, so where we do nothing, is not in the language. So this is not a valid system run. And the same for A and B. Yeah? So because we required that there are at least 2 letters, and the second last letter is a B, so this is not in the language. But when the learner observed this gives already a coherent view of the system. So this could actually be the whole behavior. So in fact, in the table we have 2 parts. We have an upper part whose rows correspond to the states, to the nodes in the graph we are looking for, and we have a lower part. And the lower part will tell us what the transitions are. So for example, from the upper part, so in the row, the only row that we have, we go with an A to 0. So actually this is the state 0. We go with an A to 0 and with a B to 0. So this gives us a coherent view already. And we can come up with a first hypothesis automaton. That's what we do here. So we have 1 state, and we have 2 transitions, 1 for A and 1 for B. So this is our first hypothesis. So what do we do with this? So we can not only ask membership queries, but also equivalence queries. So we can ask whether, well, this hypothesis is actually a system representing the unknown target language. So we can ask an equivalence query. And in practice, this will correspond to some sort of conformance test where we can send test sequences and check whether both systems, the automaton, the hypothesis, and the language agree on these test sequences. So ideally, we will have some guarantee if this succeeds, maybe probabilistically. And on the other hand, if this doesn't succeed, then we will get a counterexample for the equivalence query. For example, a BA, which is a word that is in the language, of course. The second last letter is a B, but it's not accepted by this automaton because this is not a final state, which I should have said before. So it doesn't accept anything. So this is a trivial counterexample. So this counterexample will be added to the table. So I don't go into the details. So there will be some consistency checks here. So the table turns out to be not consistent. So we have to ask more membership queries. So every entry that we have here corresponds to a membership query. So we will enrich this table and so on. So we will create new states, as you see here, because well, states that must not be considered equivalent, they will be split in this algorithm. So we get more and more states until we converge against another hypothesis. So which will have 4 states because we have 4 rows in the upper part. And it turns out that this hypothesis, this finite state representation, is equivalent to the language we are looking for. Because in particular, when we are in this state, so this means that the last letter was B that we read. So whatever we read next, so we will be in a final state. Yeah? And so therefore the equivalence checks or the conformance check in practice will succeed, and we have a model of a system to which we can apply model checking. Okay, so this is how Angulin's algorithm roughly works and how it's embedded into a verification framework. Okay, so this has successfully been applied already to a number of use cases, mainly in academia, but so learning-based testing at least is also used in industry. So I think Siemens and Volvo used this. But it has been applied to smart cards, network protocols, so they're really practical examples. And we will now try to apply it to recurrent neural networks. So recall that they can actually be considered as binary classifiers, yeah, and that the approach also applies to binary classifiers, not only languages, because this is in a sense equivalent. So we only need a very abstract views of recurrent neural networks, which are actually given by a function that map a state vector and an input vector to another state vector. Yeah, so that's actually all we need to know about this. And if moreover the input vectors actually encode a finite alphabet, because we only deal with finite alphabets, so these letters A, B are from finite alphabet, well, this can be extended to a mapping that maps a state vector and a word, a string over this alphabet to another state vector, where we just apply successively this mapping to any letter in the string. And if moreover we have another mapping that tells us for every state whether it's rejecting or accepting, then we indeed have a language acceptor or a binary classifier. So it accepts the language of words, the set of words that are mapped, well, starting with an initial state that should be given to a state that is accepting. Yeah? So binary recurrent neural network is nothing but a language acceptor or binary classifier. So in principle, this should, our approach of using Englund's algorithm, but it's not our approach, very classical, but this approach should work. So the question is now, what does correctness mean for a recurrent neural network? That's the first question to ask, probably. And there are several options, indeed. So we could specify correctness using such a transition system, a finite automaton E, a regular language, over the same alphabet, and then require that the language of the recurrent neural network be exactly the language of this automaton. So E for exact or equivalent. So this could be a bit restrictive, because this means that the language of the recurrent neural network is a regular language. Yeah, it's recognized by some finite state automaton, and this may not necessarily be the case, because these recurrent neural networks are, depending on the architecture, quite expressive. So think of XML documents which seen as a string language are not regular anymore. So this is a context-free free language. And so this could, so it goes beyond the regular languages. So this would be quite restrictive as a specification, but there are other choices. So we could, for example, specify correctness in terms of finite automaton n, so n for negative, and require that each word in the language of n must be classified as negative. So in other words, R does not produce false positives in that case. Yeah. And equivalently, we can say that the language of the recurrent neural network is entirely included in the language of the complement of n. Yeah. And so we can very easily complement the deterministic finite automata by switching final states. So we reduce this correctness problem to an inclusion problem, like in model checking, actually. Yeah. And symmetrically, we can assume that the correctness property is specified in terms of a deterministic finite automaton P. Now P stands for positive. And we require that each word accepted by P must be classified as positive. And then this is equivalent to saying that R does not produce false negatives. And again, we can reduce this to an inclusion problem and say that the language of the complement of R, which is obtained by inverting the outputs of the recurrent neural network, is completely included in the language of the complement of P. Yeah? So in both cases, we reduced correctness to an inclusion problem like in model checking, and this gives us hope that we can actually apply our algorithm that we saw before. So a little example maybe. So assume that the recurrent neural network is supposed to recognize XML documents, or a very simplified version of XML documents, where over a finite alphabet only, where we have we can create lists, we have an opening tag and a closing tag, and we can create items. Again, we have an opening and a closing tag. So this is an XML document, yeah, and which can be seen as a string, but the whole language of XML documents is not a regular language. In particular, we have to have the same number of opening tags as closing tags, so this is not a regular thing anymore. But So we can give very natural regular specifications. For example, a negative specification in this case, saying that the recurrent neural network should reject a string if, well, there's an opening tag that is not eventually followed by a corresponding closing tag. So that seems to make sense. So we can represent this specification as finite automaton as desired. So for example, here we would go with list to state that that is accepting. It's accept because there's a pending opening tag list. Yeah? So it's negative specification. And similarly here we would accept because we have a pending opening tag item, and here we would have even 2 pending opening tags list and items. So at least 2 pending. And so here are examples. So this word should be in the language of n, because while this item is not followed by a corresponding closing tag, and well, this word is not in the language of L, because but this is okay because these 2 items are eventually followed by a closing tag. Yeah? So we don't count the items because this is not regular anymore, that we cannot handle. This would be something for future work. But at least we can exclude that this is classified. So at least this is, okay, it's not in this negative specification. But we can also consider this in a positive sense. So recall that we have to check that the language of the recurrent neural network is completely included in the language of the complement of n because it's a negative specification. And well, the complement is just obtained by switching these final states. Yeah? And well, so in all the cases, we have to check inclusion of a language of a recurrent neural network in the language of a deterministic finite automaton. So the question is how we can do this. And there are several natural possibilities. So one is to apply statistical model checking or random sampling. We just sample random words and we check whether these words confirm this conjecture or whether they refute it. And if there's a counterexample, then it's a real counterexample. But of course, we cannot know, having a finite set of samples, that this relation really holds. But it's with a certain probability that it may hold for an underlying distribution. Yeah. Second approach is that we just saw. We built an automaton abstraction of the recurrent neural network, and then we apply model checking to the resulting graph. So both have shortcomings, and later on we will propose another approach that interweaves the learning task and the model checking task, so that we can maybe come up with shorter counterexamples and to come up with them a bit faster than the other approaches. So just let me go into the first 2 approaches. In statistical model checking or random sampling, we will fix 2 error parameters, epsilon and gamma, and then we sample a certain number of words, which is given here. So I think so if we have 5% for both parameters, we will have to sample around 700 words, if I'm not mistaken. And so if for some of these words, it's the case that the word is in the language of R, but not in the language of A, then we have a counterexample for sure. Okay? Then the property does not hold. Okay? So what happens in the other case? So we cannot be sure that the property holds because we only consider the finite sample, but with probably at least 1 minus gamma, we know that the system is epsilon approximately correct, the recurrent neural network, meaning that the probability to draw a word that is in the language of the recurrent neural network, but not in the specification, is very small. Okay. So the disadvantage is maybe that this relies on a probability distribution, which is not necessarily naturally given. So if we consider XML documents, so what would be the probability distribution? I mean, we can fix some distribution, geometric function, but it's not clear what this actually means. But at least, well, it gives us a feeling about what correctness means. At least we have some guarantee, even if it's not very natural. So depending on the accuracy that is desired on these parameters, we may also have to sample very many words, which may be expensive. So the second approach was build an automaton abstraction and then apply model checking. So we built the abstraction and then apply model checking. The problem here is that which I mentioned already, is that the language of a recurrent neural network is not necessarily regular. Yeah? Consider these XML documents. It's not necessarily regular, and this unfortunately means that this learning algorithm is does not necessarily terminate Yeah, so it may run forever without any result, without any guarantee. And for that reason, there is a recent paper that proposes to impose a bound on the length of the membership queries that we can ask, and also on the size of the hypothesis that we come up with. And then we just will just conclude. Either we conclude with model checking or with the counterexample. Equivalence queries in that case are implemented as by statistical model checking again, which gives us some guarantees in terms if the equivalence check succeeds. Sorry. So again, the disadvantage is that it relies on a probability distribution. And there's another disadvantage, which is that the counterexample may be spurious. Even if you get a counterexample, as it relies on random sampling, well, the equivalence, a counterexample may not even be classified as positive by the recurrent neural network, so it may not even be a counterexample. So we don't have guarantees in that case either. Another approach was, sorry, how much time do I have left? 5 minutes? 10 minutes, okay, that's perfect then. That will be enough. Yeah. So another approach, a different approach was recently proposed by Weiss et al., who do not implement equivalence queries by statistical model checking, so they don't have this disadvantage that they have to have a probability distribution, but they perform equivalence queries with respect to another abstraction, which is learned along the model, but with an orthogonal kind of learning, which involves machine learning methods, actually. And, well, if this succeeds at some point, then we take this abstraction and we perform model checking. Otherwise, again, we will have a counterexample. And, well, if this counterexample agrees, or if the abstraction and the recurrent neural network agree on the counterexample, well, then this means that we have a mismatch between the recurrent neural network and the model, so that the counterexample can be used to refine the hypothesis. Yeah. If, on the other hand, the counterexample, if they disagree, of course, then the abstraction is not correct, and we can use the counterexample to refine the abstraction, but with an orthogonal kind of learning, which uses some machine learning, support vector machines. And while the strength of this approach is that we have true orthogonal kind of learning, which will create some synergies and will allow both systems to converge to the same automaton. And then we apply model checking once the equivalence query succeeds. But we don't have guarantee that this terminates, of course, again. And a lot depends also on the initial abstraction that we have to choose, but there are some good heuristics to do so. The positive thing is that this does not rely on probability distribution. But again, counterexamples may be spurious because, well, the abstraction again depends on, well, equivalence depends on the initial abstraction. Okay, so we don't have guarantees here either. So some preliminary experiments suggest that well, statistical model checking, though it finds many mistakes actually, it takes a lot of time. Yeah, so depending on the error parameters, we have to sample a lot of words here, which takes time, of course. And moreover, automaton abstraction and model checking, though it finds a very short counterexample, takes even more time. And that's not surprising because we first have to come up with a model, so we have to learn the model, which takes a lot of membership queries before we do this model checking. But then we get shorter counterexamples. So let's look at a property-directed verification approach, and which hopefully allows us to find a good trade-off between the size of a counterexample and the number of membership queries to ask. Since heavily inspired by black box checking, which is used for systems, not for recurrent neural networks, but it works in principle for recurrent neural networks, and whose idea is to interweave the learning and the model checking task so that we perform model checking earlier, which will maybe allow us to find counterexamples earlier and to apply less membership queries. So again, we learn a hypothesis, yeah, as before. But But recall that the hypothesis already shares some characteristics with the recurrent neural networks. It was based on some observations that we made on the recurrent neural network, so it has some characteristics already. So instead of sending it to an equivalence query, it will undergo model checking. Yeah? So we'll check whether the language accepted by the hypothesis is a subset of the specification. If we are lucky or unlucky, it depends on the perspective. So we find a counterexample for this. That is a word that is in the hypothesis, but not in the specification. And if we are even more lucky, then we find that this is a confirmed counterexample, confirmed by the recurrent neural network, because then this is a real counterexample. So then we know that the system, a recurrent neural network, is faulty. Yeah. Or maybe correct because yeah, it's faulty. It does not satisfy the specification. But if it's not a confirmed counterexample, then at least we know that there is a mismatch between the recurrent neural network and the hypothesis, so we can again use the counterexample to refine the model. Okay? If, on the other hand, the model checking procedure succeeds, so we do not perform an equivalence check, but only an inclusion check in that case. Because, but suppose that the recurrent neural network satisfies H, not the specification, but the hypothesis. By transitivity, we know that it also satisfies the specification. Yeah. And this is implemented by statistical model checking because we don't have anything better so far. Yeah. But at least this would give us some guarantee in case it succeeds. Okay. So otherwise, if this inclusion check does not succeed, then we can again refine the hypothesis. And well, the experiment suggests, in fact, that this approach comes up with short counterexamples in a reasonable amount of time. And that's not surprising because we apply model checking earlier than the other approach. So it's interweaved. So learning and model checking are interweaved in this case. So now one may argue that right, it's not surprising that we get short counterexamples, whereas in statistical model checking we have long counterexamples because we sample words according to some distribution with an expected length of words that is maybe quite long, which is the case here. But it's also the case that our counterexamples can be generalized to longer counterexamples because they often form a loop in the product of the hypothesis and the specification automaton. And by pumping this loop, we can create very, very long counterexamples. And in turn, this means that, well, very often it's the case that long counterexamples have short explanations. And this is why this approach is quite appealing. So even long counterexamples can be broken down to shorter ones. So it gives us a better explanation, our family of counterexamples for faulty recurrent neural networks. Okay, so that's it already. So what I tried to tell is that the extraction of finite state information from recurrent neural network is quite challenging, but also very valuable endeavor, and can contribute to the verification of machine learning components. Well, the particular approach of property-directed verification can help to find short counterexamples in a reasonable amount of time. So what else? So what we are looking for is practical applications for this setting. I mean, I was talking about XML documents, but that's maybe not very practical, not very interesting example. And but recurrent neural networks are more and more used to control agent environment systems, cyber physical systems, and we hope that so this approach may be applicable at some point to this kind of systems. And well, coming back to the example of XML documents, so we would like to have specifications that go beyond regular languages because of the inherent expressive power of recurrent neural networks. So let's maybe look at context-free languages. But the learning tasks are not ready yet to cope with this. So there are a lot of challenges left. So that's it. Thank you.
Thank you. We have time for a few questions.
All right, thank you for this very nice, very interesting topic. I think it's quite promising, and it's different from many things that I haven't seen in machine learning. So I think it's worth it to push forward this and explore.
Great, thanks. Yeah.
I have a question that I think I mean, a lot of this relies, as you were saying, on the exploration, the queries that you can do on the input of the model, right? So you need this type of sampling somehow. You need to explore different inputs to see the observations of the system and see what's happened.
Yes.
Is there any, and then of course, if you're dealing with high dimensions, like for example, each input for your model, it's, I don't know, 1,000 real numbers. So then that could be an issue.
Yes.
I mean, at least a practical issue. It
Yes.
doesn't have to be a theoretical, but it's clearly a practical issue. So are there any results that tell you an order on the number of samples that you will need in order to check this type of approximated result with epsilon as a function of how complex is the model that you are checking? Something, I mean, in statistical learning theory, we will call this sampling complexity, for example. Is there any something
So the question
similar?
is, so what kind of model can be handled, right? So
Yes.
what's the complexity of the models that can still be handled? Is that right?
Exactly. For a given model that is a black box, you don't know it.
Yes.
There may be some metric that define how complex is that model.
Yes.
And then the question is how many samples I will need to use, how many queries I will need in order to discovery with a probability larger than whatever you wanted, 95%, that my check is okay.
Yeah. So I can tell you a little bit about what's necessary or what can be done in the setting where we have finite state systems, not recurrent neural network. And there a lot depends on, well, there are several parameters coming into play, so the number of states of the model, but also the size of the alphabet, which is actually crucial. And you talked about these inputs, and that's related to the size of the alphabet. So here we have A, B in the example, for example, which is quite manageable, but usually systems have many more inputs.
A huge number.
And this is a crucial parameter so far. The problem is that this may even be infinite, right? And so if you have cyber-physical systems, maybe you have time-stamped and so on, then we have to find good abstractions of that. And that's one of the main challenges in this area, to find good abstractions that preserve the property in a sense, so it's sufficient to check the system for this kind of, for the small alphabet, for the small inputs, and that is still manageable. So far, I think rule of thumb, sorry, it's that you can handle an alphabet size of 100, say.
All right. Okay,
so I mean, it's not bad already, but it also depends on the size of the model. So so usually we assume that we have an upper bound on the number of states. We don't know precisely the number of states of the model, but we have an idea of the state space, and we give a conservative upper bound, and then this allows us to come up with a test suite that is correct and complete and. But still, so in practice, the system that we can do in practice are quite small. But the number of states and the input are crucial parameters, and the main issue is how to reduce the alphabet, and that's, I guess, your question. And for recurrent neural networks, it will be the same, I guess, and even more for systems, for cyber-physical systems, if they control this kind of systems.
Thank you.
But that's all I can say for the moment. Yeah.